Hello, this is Sarah Martin alongside Asingwe Eric, and today we are going to be talking about explainable AI or XAI. So, uh, previously, previously, back then, there used to be we had very many machine learning models, especially the complex ones such as deep learning, termed as black boxes. So, a black box is where an AI model makes a prediction but you don't know what it was basing on to come to this conclusion. So black boxes were kind of like anonymous decision. You don't know why the model is making such a decision. You don't know if it's maybe trying to classify a cat. You don't know maybe it used how many legs it's seeing in an image or the features that it's basing on. So we were blindfolded about trusting such decisions. And this was the major challenge of this black box model. So we couldn't trust the model predictions because we don't know what the model was basing on. We had it was very hard to debug and improve the models because of the same issue. Then it had bias. So and as well as to comply with the regulations. Then with these challenges coming into play, something called explainable AI had to be the best solution for this. So explainable AI is where we're getting to know why the model is making these predictions. So, explainable AI aims to make machine learning models more transparent and understandable. So, it also provides insights on how the model is making their decision. They know have techniques. Since our project is about EEG data, which is a time series data, we opted for these XAI techniques such as feature importance, sharp, lime, rule extraction, and partial dependency plots. So uh, let's take a look at some of the techniques that we used. And this is the permutation feature importance. So one of our best performing models was the recursive neural networks using the GRU computation. And when we look at this, we're trying to find the important features in the data. So the way the way permutation feature importance works is that it gets as the model is making the predictions, it gets these specific features and tries to randomize the value as it sees the outcome it causes on the prediction. So if the slight change of this value causes a higher prediction bias or a higher change to a certain outcome. So it means that feature is important than the others. So due to our data set being large, we had to first carry out PCA to kind of scale it down to find the most important features. And when you look at the graph that was generated, you're seeing that feature 4 had the highest importance, and then it went on reducing accordingly up to the seventh feature here. So this axis, the x-axis, represents the feature index, and then the y-axis represents the importance or the accuracy drop. Then the bar being the value of the importance. Yeah. So with that said, the next slide, my colleague can continue from there. Thanks.
We shall be talking about sharp analysis in erosion base and decision trees. Now, as we can see, both we have a plot on the side. That was the sharp analysis summary plot. I think I'll talk about it. It is this was applied on the training data and it shows the different principal component PC. Then on the model, there's the output of the classification of the different PCAs. From there, the the RNN, sorry, first, sorry for that, network, sharp analysis on LSTM. Then this is powerful sequential data. It uses a time series, and these are great for tasks like uh, evaluating the waterfall plot as we have down there. Then the feature contribution we have at Sharp, it helps to understand how features at different times steps influence in the LSTM prediction. Now the interpretability in this is then the other results that we attained from that using the Sharp analysis on naive base, we got this shows the feature importance of different features. The x-axis has the minimum absolute sharp value, represents the average impact on each PC and the model's prediction. Higher values indicate greater importance. On the x-axis, we have the principal components lists, the individual principal components, and from 0 to 100. Then we have the bar heights that represent the absolute sharp value. Then the next one here we had our heat map that also represents the feature importance on the LSTM. The x-axis, the y-axis has the accuracy drop and how much the model accuracy decreases with a feature randomly shuffled. At a higher value equals to more important features, similar to the previous one that we had. The x-axis lists the features ordered from the most least important, and the box plots that we have there, they show the distribution of importance scores across the multiple permutations. The key for this is on the side there. Then lastly, our last slide, we have this also as a permutation importance showing the feature distribution, the feature importance distribution. On the axis, we had also the accuracy drop, showing how much accuracy keeps on decreasing. Then we had the feature index on the x-axis, sorted from most least important. Then we have the box plots, showing importance of each feature represented by a box plot, showing the distribution and the scores across multiple permutations. This has been Asimile Eric and Barry Smarty. Thank you.